In the previous video in this series, the Dirac equation was used to learn more about the working and role of matrices in the equation and matrices in general. In this video, the same thing is done for its role as a differential equation and as a particle equation in quantum field theory. It is shown that neither the Dirac equation nor quantum field theory truly describe what lays outside of the particle, the thing called space or fields, and what the boundaries are. And that when combining particle and field, numerical methods are preferable, all the while using simple models. In the end, as a bonus, this is taken to its ultimate conclusion, to the point where physics and mathematics meet each other for the first time. So let's first recapitulate the mathematics correspondence principle, which applies to any mathematics, so also to the general class called differential equations. But what, by Jove, corresponds in nature with something like a differential equation? There is no one sitting on the moon that has all available data on the position of the moon, of all the influences that work on the moon, and of all the mathematics that one has to apply in order to calculate what the orbit or the trajectory of the moon will be. And the same goes for any human on Earth who wishes to do the same thing for the artificial moon he is going to launch. Everybody a bit familiar with these technical things know how this is done. It is done by successive approximation. The point in space where the spacecraft is known, the forces that are working on it are known, and the position of the spacecraft a small time later is calculated from that, which, as everything before, is an approximate number and requires course corrections. And this is applied successively, which works well enough to land on the moon if you take steps that are small enough. And this is a summary of all this talk. Nature doesn't solve differential equations. Nature solves successive approximation calculations for infinitesimal small steps. Here is an example in the form of the essential part of the code for a successive approximation simulation of a harmonic oscillator in the form of a mass on a string, which gives a perfect reproduction of the movement of a harmonic oscillator. So there's your choice. You do this or you do that, this being the differential equation on the left and that the numerical calculation on the right. The way nature does it is on the right, says any common sense. Or like this in more formal terms. Physics is something from nature, mathematics is something from humans. Now let's learn an immediate lesson from this with this new case. One could make it into a puzzle. Find the differences with the previous one. The answer is that visually there are two occurrences of the same difference. T is replaced by X. Conceptually there is no change, and in the code there is no change, because the symbols in the code are completely arbitrary. So conceptually there is absolutely no change at all. The immediate lesson: in such simulations, the symbols have absolutely no meaning. One step further, in such simulations the symbols have absolutely no physical meaning. Followed by the superfluous next one, in the corresponding differential equations, the symbols also have absolutely no physical meaning. And finally, in mathematics, the symbols have absolutely no physical meaning by themselves, which we already knew, though it is nice to see it confirmed again. And here's another gain. If the left equation can be solved with successive approximation, then why not the right one, which has no conceptual difference with the Klein-Gordon equation? Use Ct instead of t, change some signs and constants, and there you are. And why not this one, which is the fully fledged Dirac equation, written out in its components, or any of its alternative formulations? Or use this idea from the previous video as a starting point, put two samples of Dirac code on the diagonal positions, and one can start playing with the interaction terms on the non-diagonal ones. But the Dirac equation is a continuation of the de Broglie oscillation, as seen in the previous videos in this series. And the Debye oscillation is just an assumption. There is no justification for it in physics, other than that it gives the right results, as Debye himself writes down explicitly as the quote shows. And this situation hasn't been improved upon since. As had to be found out here on YouTube, where colleague Nick Lucid, after explaining that the Schrödinger equation is not a wave equation, explains that a wave equation has a second-order derivative in space that acts as the curvature of the relevant function at a certain position. And that this curvature is the thing that causes an acceleration, the other term, that drives the function back to its equilibrium position. Which equilibrium position it reaches having its maximum velocity, so that it continues past its equilibrium, etc. At which point the mathematics correspondence principle is applied, resulting in this corresponding physical model. The illustration had to be made specifically for this occasion, because no similar one could be found, though it is completely standard physics. There are plenty of the kind that uses rows of vertical strings like the ones we use for the Debye model on the left. In fact, doing it in 2 dimensions is regularly encountered for quantum field theory, as shown on the right. However, putting the two models side by side immediately shows that there are fundamental differences between them. First of all, the individual oscillators are not connected. They are hanging from some common platform, but what is this common platform? Does it exist, and if so, what are its properties? Though a specific one can be guessed, if it does exist, it must be infinitely rigid, or else the oscillators would influence each other. And otherwise there seems to be no connection, so no continuum, especially when viewed from the stationary observer system. Again, comparing the two models, it is almost as if the whole process has been given a turn, or conceptually, that they are perpendicular to each other. And remarkably, this too can be put into physics. Take the separate oscillations of the Debye, turn them 90 degrees, and connect them with each other, giving the illustration. This makes the two models seemingly identical. So now we have two processes, the basic oscillation as introduced by the Debye, or parallel uncoupled oscillators, and that of the strings in a continuous line connected to each other. The first works as a source, the second as a continuum that acts as a neutral propagator of the disturbance caused by any oscillator. Which, one would think, must somehow be connected to each other. Like neighboring points in the continuum must somehow be connected to each other, one would think. And this is something one can model. The numerical approach to the oscillator we have already seen, so that is now simply a sine function. Then comes the loop with the code for the propagation of the disturbance through the string. Just pass the disturbance to the next door neighbor. Here done in the simplest way possible, because that is the only thing necessary for what we wanted to prove here, the proof of the statement that no harmonic oscillators are necessary for propagation in the continuum. And finally, a separate third and crucial step, the code which connects the two. Here's the live version, where on purpose the two are not connected, because that is conceptually a different process, and filling it with another color would not be conspicuous enough. The concept itself is dealt with later. Now let's have a look at the slightly less simple standard approach to the problem of waves on a string, found with the help of AI, which uses the standard method. It translates the second derivative into finite numerical differences. Here's how this code works. On the left, the difference of the transverse displacement and the associated force at a given point with left and right neighbor gives two longitudinal forces to left and right, which when combined again gives the transverse one on the right. In the drawing, liberties have been taken with the signs of the vectors and subtractions in order to highlight the principle. This is the physical illustration of the mathematical formulation that the curvature, the second derivative, leads to a restoring force. And never in this story is made any mention of harmonic oscillators. Here is the result of the comparison of the two approaches. The simple one at the top, the slightly extended version in the middle, and their difference at the bottom. And this is the AI solution to the coupling of the two processes. It is exactly the same as the simple one. It is just defining an equal disturbance at the point of contact. So there is no physical process connecting the two. But one can already play with the process of propagation in the continuum. Here again is a simulation, but now with a really novel phenomenon visible, of which it would be impossible to guess the code. Here on the left is the regular code of the propagation, and on the right is the new one. It just changes the taking of the differences one step further to the right. The effect is highly sensitive to the value of the coupling constant. What you see with the used values looks like a single excitation, suitable to describe a particle, probably due to the fact that UI is present in it, so leading to some kind of self-interaction. We will come back to that later. In fact, what we are encountering here is the wave-particle duality, as seen earlier. The oscillation is the Dirac oscillation, which becomes the Dirac equation, whose wave functions obey the exclusion principle, thus leading to the reflection of them by other particles, leading to the two-particle interaction used to solve the quantum problems and entanglement, as shown in the previous series. To the continuum apply superposition as follows from the wave equation. Two solutions added also form a solution, and their only definite property is that these solutions propagate with the velocity u, which in fundamental physics is almost always the speed of light. However, this is a property that has to put in by hand, as it is done in the simulation by choosing numbers, and doesn't follow from the equation. So now over to the matter of the boundary between the source oscillation and the continuum that propagates this disturbance. Of course, one would like to equate the source oscillation to a particle, as de Broglie did, and to introduce the frequently enough used imagery of some sort of knot in the continuum. Or some kind of vortex, as in these illustrations. For a one-dimensional string, it is hard to see how this could be done. However, leapfrog to a continuum that is three-dimensional, apply the fixed point theorem of Brouwer that says that in any disturbance in an environment with some kind of boundary, there is at least one point that remains in the same position, and there you have a large part of how nature seems to work. As particles that are disturbances around the fixed point that remains localized around this point. As stated, for this kind of result the single string model seems too simple. But this changes if you take into account that we are still talking about the Dirac equation. And the Dirac equation has four components. So one must make a string model, not with one, but with four strings. Add coupling between the strings, or components, and one immediately gets structural properties, like in the example shown. And coupling between components is precisely what the Dirac equation does, as the written out version shows explicitly. Now for the Dirac equation we know that it includes spin, in the form of a coupling between the two components that form the upper pair, and the same for the lower. And, as we have seen previously in this series of videos, the essence of the Dirac equation is that upper and lower halves are exchanged. Apply this to the mechanical model, and there you get this illustration. Now isn't that a happy coincidence? The components make a point in the middle. And this was neither foreseen nor planned. The picture illustrates the symmetries that Dirac has put into the equation. And here not included are effects of possible relative phase differences between the components, of which in the previous video in the series has been suggested that they may represent charge. So now we have two kinds of four-string model, one without coupling and one with. And wouldn't it be logical to equate the first one to the continuum and the second to the particle? In which case you get this for a particle in a continuum if one simply combines the two in a mechanical way. But nature of course works with continuous processes, of which the first two steps are shown. So with having 4 strings or 4 components, we now also have 2 kinds of oscillation, one with internal coupling and one without, or equivalently with more or with less coupling. And we have a first step towards a connection between the two. Having both something that may represent a particle and something that may represent a disturbance or wave in the continuum that surrounds the particle, it is also possible to add the process of interaction between particles to the model, as shown. For clarity, the old-fashioned mechanical version of the border is kept. By the way, what you see here is that 2 quantum systems being coupled to each other is the universal case. What is called entanglement is just a case of measurable coherences at the macroscopic level, similar to the double-slit experiment. Now if there is some process that is working within the particle that keeps it together, a reduced or otherwise related form of it might also be present in the continuum. That might occur through coupling between components or through phase effects, but because the latter are difficult to show in the illustrations, we also use the former one for the latter. Perhaps one could use color, but it is too complicated for now. Also note that nobody guarantees that the propagation velocities of the different components are all the same. There are 2 known basic variants of this interaction. For spin is 1/2 particles, it leads to the 2 particles excluding each other from their own space. And for the aspect of charge, there are the 2 known possibilities of identical and opposite charges. But the underlying process is the same for both cases. The disturbance in the continuum makes the particles change its state, and this change in state leads to an acceleration of the particles towards or from each other, something that humans translate in the terms of force. Here's another illustration of the interaction, now including a change of state of the particles. This state then corresponds to an increase or decrease in the change of position per time period. On top for attraction, on the bottom for repulsion, or the other way around. And this might in reality be done through phases, but these are difficult to illustrate and cross-coupling does that more clearly. For the case that is called the exclusion principle, illustrations are more difficult. Here is an attempt. What this makes clear is that for the given fact that the particle, the electron in any case, forms a stable whole, there has not been found any further detail other than what we know, that it results in a stable oscillation. The demand for having a stable structure can be formulated in a more general form. Find a combination of structure and vector such that at some closed surface its values are 0. Then you have a stable state or particle. There is an example of this in atomic physics. In order to solve his equation, Schrödinger in effect used the boundary condition, equivalent to using the Laplace equation, on the left, both of them giving the spherical harmonics that also describe the atomic states, on the right. Something similar can be investigated for fundamental particles. The likelihood that this can be done through analytic means, in its initial stages anyway, is not very high. The illustration on the left attempts to show the insolvability of the 3-body problem, which also applies to celestial mechanics. And on the right one sees the so-called Antikythera mechanism, a device from the time and environment of Aristotle, using mainly gears, that predicts all kinds of celestial phenomena precisely enough for everyday usage, decennia and more in advance. A numerical calculation, as in this basic example, is precisely like that. A number of gears, lines of code, driving each other. This should be enough to give an idea of the route that is suggested here. For a large part, it boils down, besides the already mentioned more or less technical suggestions, to giving a much more active role to what is generally referred to as space, or the vacuum, etc. The nasty thing is, of course, that it all looks terribly much like talking about an ether, but it cannot be helped. It is inevitable to discuss the thing as soon as one accepts the model of the Braille with its infinite propagation velocity. But let's be honest, the standard vacuum is a nothing. A nothing can do nothing. Our thing propagates electromagnetic and gravitational fields. So our thing does something. So our thing is not a nothing. So our thing is not a vacuum, and its name should be replaced by the continuum. But now that we have a route towards an alternative, it is time to have a look at what it tries to replace. Is that something having value? It is usually insisted with great emphasis that this is so. Quantum field theory is the best theory we have. Look at how accurately it predicts measured outcomes. Repeated thousands of times, here in the version of colleague Arvin Esch, who summarizes it perfectly. And the illustration almost says it all. The first thing it shows is the conceptual likeness to the model of the Braille, where the simplicity of the latter immediately shows a fundamental drawback of the former. Where are the fixed points that the masses are oscillating relative to? The de Braille model is merciless. It must be against some common solid background. However, Ash makes an improvement on the Braille. He adds a connection between the springs. Now we can add more springs in a line and connect them with rubber bands. But this is just didactics, a step to make something clear for the more or less layman's public, because shown are two steps from the mathematics that show the Hamiltonians or energies used. Absolutely no rubber bands there, just terms belonging to the oscillators. Rubber bands carry energy, and that energy is not in the Hamiltonians, so nor will the bands be in the wave functions. The physics remains that of isolated oscillators. So that is the conceptual state of affairs regarding quantum field theory. When trying to explain what happens, one has to take refuge to connections that in the physics aren't there. One other example of it has been observed. Rather hopeless from the start, one would think. But Arvin Esch should be praised for realizing something that standard theory refuses to acknowledge. So there is only one thing that connects the strings together, the solid background. Conclusion: so far the model is circular. It tries to describe a common background with separate oscillators, but needs a common background for the oscillators. Which doesn't solve the problem a bit, but sweeps it under the carpet. But there is more. This is the well-known outcome for the Hamiltonian after quantization of the oscillators, also used by Ash, with the A operators rising and lowering the energy in discrete steps, and with the constant term of 1/2, which, after summation over all possible oscillators or integration over the entire relevant space, becomes infinite. And this applies to any situation, because the separate oscillators are infinitely small. This has unleashed an entire program to remove these infinities, called renormalization, which boils down to creating other infinities and subtracting the two. Here's an example of what one can get if one allows this. Add all positive integers together, and the sum of it gets a negative. One can look it up for oneself to see how it is done, but the essential error is that one takes two copies of the same infinite series and shifts one of them one position relative to the other, which is not allowed because that isn't a simple change, but amounts to an infinite number of changes. One can say that it is not allowed to subtract infinities from infinities in general, which should be added as a rule to the mathematics correspondence principle. Perhaps there are exceptions, but these have to be proven on an individual basis. For quantum field theory, people like Paul Dirac and Freeman Dyson much earlier also uttered these kinds of objections. In quantum field theory, The name associated with investigating the situation is Oliver Konza. Shown is a screenshot from a video on YouTube that claims to show that indeed something has happened that looks like adapting the calculated numbers to the measured ones, and not the other way around. Old-fashioned physics has a more physical and practical formulation. The fundamental error behind the approach to take a continuum and divide it into an infinite number of infinitely small parts that are somehow connected to each other is that any error in making this connection, like here in the model of the oscillating string, no matter how small, becomes infinitely large when the infinite number of small parts are glued together again. But here we have a more general objection. Quantum field theory seems a perfect candidate for an analogy with the Ptolemaic model of planetary motion. Given enough epicycles in the latter, that motion can be described with any accuracy desired. What is lacking is a common physical background for all these epicycles, specifically their centers. And this is what also seems to be the case for quantum field theory. There too, a common physical background seems to be missing. That is why Arvinesh, in his desire to explain how the disturbance of one oscillator gets propagated to its next door neighbors, had to invent his rubber bands, which do not appear in the mathematics. A really very sorry state of affairs, and one of which the cause can be guessed. One cannot write about such common background in academia, because there is no ether. So for the ones that have reached this point in the video, and therefore must be very tolerant to outrageous suggestions, here are two other ones. The first one is based on the still of the simulation on the left. Its distribution of virtual density is the opposite of the string oscillating according to the wave equation on the right. And it isn't just a simple model, because the AI version shows the same feature. One could start an investigation, but there is a one-step and therefore simple solution, that the points represent negative density, that is, one lower than average. Then model and wave equation correspond. And in the context of the Dirac equation, such positive and negative pairs are common, though one usually associates them with antiparticles. And it also seems to go together better with an infinite propagation velocity. The problem of the latter is our automatic association with the propagation of massive things. Call the above idea a negative mass, and the problem almost turns around. Negative mass would lead to infinite acceleration. And by the way, the concept in itself isn't unknown. Examples are holes in a semiconductor and bubbles in a fluid that, when the hole is rotating, go towards the center instead of fleeing outwards. Highly controversial, of course, this idea of a reverse density oscillation, but it need not apply to all components, say only to those with some kind of coupling, while the others propagate with the light velocity, or the other way around. All made possible by dropping the vacuum idea and going over to the continuum. The second outrageous suggestion starts with the basic situation of the oscillation in a continuum. Where does this end? Nowhere is the answer in quantum mechanics. Yes, it ends here, says the reality, at the end of the universe. And now we can suddenly say something about the energies involved, if we recognize that in the inline springs of the continuum there is stress and strain. How much? The absolute number is not known, but for the relative number one can make a guess. The number of spring elements in a wavelength can now be compared to the number of spring elements in the entire string. That is, one has to compare the wavelength of the quantum mechanical oscillation to the diameter of the universe. Take for the quantum mechanical wavelength that of the Compton wavelength of the electron, and the calculation is basic. The outcome, 10 to the minus 40, give or take a few decimals. And there too is the relation of the strength of electromagnetism relative to that of gravity, one of the famous large numbers of Paul Dirac. Now isn't that another striking coincidence? Note that again in this story, An infinite propagation velocity for the wave is more logical than one with light velocity. By the way, gravitation need not be quantized, which is given discrete levels, at all. There are no known discrete states associated with the state of the universe, just ones for fundamental particles. So one can forget all attempts at using non-commutating operators, etc. It just needs some oscillatory phenomenon, also known in quantum mechanics, to explain it exists. The conclusions from this video: there is a strong case for putting at least as much effort into a numerical approach to a situation that until now one usually treats with differential equations. And that quantum mechanics and quantum field theory should combine the two kinds of oscillatory phenomena, active ones governed by harmonic-like oscillators, and more passive ones governed by propagation in a vacuum, and how the two are combined, which until now is completely lacking. What has here been done so far to improve on this all serves the purpose voiced by John Wheeler. Already beforehand you must have some idea of what you are doing. That means a physical idea. Old-fashioned physics accounted this from Wheeler very early in the career, in a small booklet by him on the numerically programming of harmonic oscillator in Fortran. It turns out that Wheeler also developed a wider philosophy on the matter, in which he states that all of physics boils down to yes or no questions to be answered by experiment. An experimentalist would point to one of his major tools that Wheeler omits, the error bar. This old-fashioned physicist has also long mused on the matter, and recently came up with the following as the ultimate abstraction of the problems encountered with what is a particle, in the above coming back in where lies the boundary and how do you define it. Giving the immediate result that the all possible paths formulation of Richard Feynman is a logical contradiction. The concept of particle, as in part of, implies an outside of the particle, which is the continuum, while all possible paths implies a presence over all possible positions, so a presence all over the continuum. Yes, putting it like this is bothersome to many, but that cannot be helped. There is room for corrections in the comment section. In a future video, we will involve dear Mr. Einstein in the discussion.